missing these types.
Yeah.
It's not dangerous. I've never seen structures like this. I mean, for
But usually they use peaceful.
yeah,
Because
it's not fast.
It's
It's not
not
fast.
But fast, they don't have that much power.
It's not. It's a piece usually electric.
They might be having honey.
Yeah. So I remember I was in Bangalore at this Kolomeisky on the campus. So we were working on a huge structure, termites.
Termites.
They made something huge. It looked like a stone. And the termites
Those sort
here.
of structures usually appears in Rajasthan.
Oh,
We have sand
that's
over there.
I've never been there. First time I've seen it. There are termites in Texas, but they never make structures like that. They're dangerous. They infect your house and just.
We have companies who treat houses if you have termites. We have lots of issues.
And so
Some parties.
for the most house. Thank you. We're on time, right? Okay, thank you for staying alive. Let's go to lecture number 4. Again, feel free to ask me any questions. We'll try to move slower. I prefer do not oversaturate you with information. Let's try to move. So what we do, we'll talk about some specific examples. So remember the plan. Remember the plan. The plan was, the beginning was something about kinetics, introductory, and we got some tools. Tools were discussed in the previous lecture. What we will do from now on, we will learn by examples. We will consider 9 different examples of systems where stochasticity, randomness is important. And then we'll try to figure out, learn what can we see about stochasticity, what we can understand. So most of this study is based on what I did, but with addition of what other people did. Okay? There will be, for each case, I will have to explain a little bit more for each system, details, which probably not necessary, but that's a way for you to understand what is going on. Okay, so this is a story, chemical story. Will be 1 chemical and 8 biological stories. So this is a chemical story. This is a story about cooperative communication with a single nanocatalyst. So we already talked with you about catalysis, right? So catalysis is a set of physical chemical phenomena that allow to accelerate reactions, chemical reactions, which are usually slow. Catalysis has huge applications everywhere. So $10 trillion is associated with the catalysis. Catalysis is everywhere in production of drugs, in production of oil, gasoline, in production of toothpaste even. There's a lot of things that people use. And cars, you still have gasoline cars in your exhaust. There is a platinum cover on your exhaust as a way of making sure that the final exhaust is a carbon dioxide in water to clean the atmosphere. So anyway, so we generally understand, as already mentioned, we generally understand what catalysis does. It creates a different pathway for reaction. If the original reaction has a very high barrier, catalysis creates additional pathway, and that's what allows the reaction to accelerate. But so while we understand the general features, the details, molecular details are frequently not well understood. And it's especially difficult to think about the systems which are some which call heterogeneous catalysis, when these reactants, products, catalysts, they are in different phases. Okay, so the biggest problem for understanding catalysis is this heterogeneity. The surface where reaction happens is extremely heterogeneous. At the same time, most of the measurements, experimental measurements, are so-called ensemble measurements, bulk measurements, kind of mean field measurements. And the phenomena also very complicated. There is an electron transfer, charge, diffusion. It's quite a complicated phenomenon. So this picture, I wanted to show you how rough a surface is. This is real pictures, atomic for microscopy done. This is alloy nickel molybdenum, one of the popular catalysts, and this is another mixture of the catalysts. So the surfaces are very, very rough. And the problem is, so the active sites clearly will be very randomly distributed, very heterogeneous. So this, by the way, this is a popular catalyst for hydrogen production. There are cars in India which run on hydrogen, no? BMW is producing some of those. And they are actually ecologically quite good, right? Because you're only producing H2O. The problem is to collect hydrogen. And it's not trivial thing. So the BMW is producing. Okay. So theoretical studies of catalysis. When people talk about catalysis, there are many different methods, but frequently people assume a very idealized picture. The picture, this is showing, okay, this is the picture that people assume. Everything is perfect and ideal, right? Just contrast this with this, right? Right? That's not what you see in the real system. So, so there's randomness, it's a random phenomena, there's a heterogeneous phenomena, the catalytic one. So let us try to look at this phenomena using stochastic approach. And again, the logic we do, like I told you before, we will concentrate on dynamics, because dynamics reflects the microscopic mechanism. That's what we will try to do here. So what is actually useful, in recent years, people started to use so-called nanoparticles. So this is a small particle that you can controllably synthesize. One of the popular gold nanoparticles, for example, and people like to use them, especially for catalysis. That's because it's much more controlled structure and composition. You can actually study them with single particle precision, and you can have a better control of active sites. Active sites are locations where chemical reactions are taking place. Okay, so I already showed you something similar but different thing. So there is a single molecule studies. You can do single molecule studies. So in this experiment, schools were studying experiments so that the products are fluorescent. Okay, so this is, you don't need to know the chemical formulas, but the product was fluorescent. So when the reaction happens, there is a spike. No reaction, reaction. No reaction, reaction. Okay. And then remember, I showed you something similar when I was arguing that chemical reactions are random, right? Rates times before reaction times are random. You can see it also clearly here. But these are nice experiments because you're essentially looking at almost like a single active site or very few active sites. You're reducing this heterogeneity. And again, to notice the stochastic aspects of reaction time, as we discussed. Okay, good. So people did a lot of experiments, and there are interesting observations, but I would like to talk today about only one phenomenon, which is interesting. It's a catalytic communication, catalytic intraparticle communication. That's the only thing I will talk today. So, and to explain it, I need to explain a little bit about the way experiments were done. Very little, I know you're most of mathematicians, but still it's easy to explain. So imagine, so what they did the following thing, that they look at this nanoparticle. This was a real nanoparticle. Total was 1 micron, over 100 nanometers in length. They looked, this was catalytic, it was made from a palladium or from gold. These people work with really good materials, expensive, but because it's very little, so it's not a problem. And they looked at these different reactions. This is called a redox reaction. It's a reduction oxidation reaction. So reactions which involve the transfer of electrons or charges. And these reactions were catalyzed by these single nanoparticles. And you look at them with a fluorescence spectroscopy. In other words, you put your camera and you look and you see what's the reaction happening, you see the light. When the reaction happening, you see the light. That's how it was done. And there is one surprising observation that people experimentally found. They found that if reaction happened in one location, let's say it happened in this is by the way analysis, right? Suppose you are after you look at the picture, you look at this segment, so they realize if reaction happens here, then in the next moment, the reaction most probably will happen in neighboring sites. It's a catalytic cooperativity. That was surprising because each active site is independent. Chemical reactions are independent. So they found that this catalytic cooperativity. Yeah, so this picture is better to understanding. So this is a whole your nanoparticle. This is for analysis. They divided in seconds, not in reality. So they were able simultaneously to look at many events, and record the time of this event. Each spike is of each reaction, and you could find the correlation. So the way they did it, they looked. So this is real experimental data. You don't need to look at many graphs. This graph, you found so-called. They look at the Pearson correlation coefficients. Pearson correlation coefficient is something that probably some of you know. So this is what is Pearson correlation coefficient. Imagine that you have some chemical reaction. There will be some average rate. So then you are there's average rate, but suppose you at some location I and J you are recording time of reaction, then you can calculate this quantity. And if you do it over many measurements, if this quantity is zero, there is no correlation. And that's what you typically expect. Chemical reactions are independent. Remember the collision, there is no. But if it's close to one, that's a strong correlation. It's close to -1, a strong anti-correlation. That was very surprising. How it can happen. So again, so suppose the monitoring reaction inside I and inside J times. And if this number is not zero, there is some correlation. Could be positive or negative here. And they found that for this specific systems, that these distances over which this cooperativity was observed was not small. It was ranging between 100 up to 600 nanometers. So remember, this is the whole thing 1,000 nanometers. So it was significant distances. And this phenomena also was up to some 100,000 seconds. Up to 100,000, just 100 seconds. So this is intraparticle catalytic communication. And there is additional surprising observation. So when people do experiments, what you typically do, you try to change some parameters and see if it will affect the result. So what these people did, they changed for given nanocatalysts in given chemical reaction. So this correlation lengths, correlation times were independent of segment. So they were changing segmentation size. Like let's say they were changing laser intensity because this is was done with the laser. They were shining with the laser. They were changing concentration of things. Nothing would change. It would be the same number for cooperativity distance and cooperativity time. That's called universality. But they were able to show that there is a catalytic communication somehow involved with some positively charged particles, charged holes. So this is strange. Okay, they were trying to do. So it's like all active. Yes.
So this cooperative behavior between these gold nanoparticles,
Which is active sites on a single nanoparticle.
So with length of the, like for example, if you have a sample with length, it reduces.
Yes, that's right. And you can calculate, you can estimate specific lengths. So this is those older several hundred nanometers. So it looks like active sites were part of a WhatsApp group. And immediately when something happens, like send a message and everybody knows. It's my analogy here, okay? But the chemical reaction at every site must be independent. So that's a controversy. It's not clear where it comes from. Okay, so these are the questions. So why and how this catalytic communication is done by this charge hole? What drives the motion of charge hole? What is the microscopic origin of this universality? And how you can quantify this correlation, length, correlation times, and this. And there's also in this experiment they looked at the effect of external fields. They repeat experiments under external fields. They change the field. They change the angle of the field. Here comes theoretical hypothesis. which is again driven by stochastic idea. Stochasticity. The idea is that, so let's assume that each active site reaction can happen. The probability for reaction to happen at each site is depends on local concentration of this charge holes. This is assumption number one. Then there are assumption number two that each site produces additional charge holes. Remember, these reactions involve charge transfer. And then if you additionally produce charged particles, then they can go away to other sites because there are more there, they go away to other sites. If they go away from the given reaction site, they temporarily increase the concentration of these charge holes in neighboring sites, and that's what stimulates the reaction. The reactions here. And this communication distance is average distance traveled by these holes, because they can disappear, they can be removed by different mechanisms. And communication times corresponds to the lifetime of this charged hole.
Actually, intuitively, what is a charged hole? Sorry if I missed this.
No. It's in a metal. Okay, so if in a metal you if you remove in a solid object one electron, so this what is left, you can call it a hole, charge hole. Okay, it has positive charge. Okay. So this is my analogy. What's going on here? Imagine that some of you or your mom is doing a lot of dough, produce a lot of things to do some bread or cake, but she produced a lot of things, right? So instead of wasting the dough, she's going and give it to a neighbor. And the neighbor couldn't even think of making cake because the dough makes the cake. So that's the analogy that I'm making this. Somehow, each reaction produces additional number of these charge holes. They diffuse because there are too many at this location, and if they refuse, they stimulate at the other location of the reaction. This is the idea. This is the idea, and this idea allows you to develop this stochastic model, this three-state stochastic model. So we can look at the one-dimensional model, and again, it's one-dimensional because the system is essentially quasi one-dimensional. The experiments were done on so-called nanorods on a one-dimensional object. We assume that the probability for the reaction to occur is proportional to the local concentration of the hole. It's essentially you're producing stochastic model. With producing stochastic model, particle can be created with some rate, can diffuse with some rate, and it can disappear with some rate. It's a stochastic model, birth, death, and diffusion. Birth in some location, diffusion, and death. That's what also described here. So each reaction produces new charge hole with the rate K. Charge holes migrate with diffusion rate and disappear with rate R. And each of the lattice sites corresponds to segments. Remember, when they did experiments, when they analyzed, they divided into segments, right? In analysis, not in real nanorod. In the analysis, they divided into segments. So each of these lattice sites can correspond to segment length, which is 100 nanometers typically. Okay, good. So yes, so this is a model, stochastic model, and let's try to continue. So suppose there is a single charged hole, single particle, produced at site 0 at time 0. So the question is, what will be the station distribution of probabilities of this particle? Okay? You can write equations which look familiar, right, to you. It's the same master equation that we had before. This is the probability to find the charge hole at site n at time t. U is the same U because of diffusion, or equals diffusion, and then there is additional term here, R, right? Because particle can disappear. In contrast to simple examples that I had in previous lectures, there is here particle will disappear at some point. But otherwise, it's the same master equation, right? The same master equation. And of course, for some specific site, there will be birth rate. I'm just not sure. Okay, you can calculate, so you can solve this problem, one-dimensional problem. You can calculate this problem in stationary state limit. Stationary state limit means that you are assuming that this is 0, and then you solve the problem. And that's a distribution of probabilities if if you're producing the particle at time zero, at side zero, that's the probability to find this particle at steady state. And it's decreasing because eventually the particle will die. But these two things actually have a exponential decay in both lengths, and this exponential decay length we can associate it with the communication length. So this length can be very well approximated as a square root of diffusion constant over that rate, and the communication time is this inverse of the death rate. Okay, so you can do these things here, and of course the best criteria for theory is experiments. These experiments measure these quantities, and we can compare with a very simple theory. So these experiments measure lifetimes of these holes, diffusion constant, and experimentally they measure this length here. So you can see experimentally measured, theoretically calculated from these quantities, experimentally measured, theoretically calculated. I think it's excellent agreement. Excellent agreement. And again, remember, it's a stochastic framework. It's a stochastic framework, and you still can explain many things here. And not only this, you can actually even simulate Pearson correlation coefficient. So in this case, black one is experimental, and the red one results of our simulation. So what we did, we made the Monte Carlo simulations, and then we essentially calculated Pearson coefficient the same way like it was done in experiments, and it does also look quite good. So we see that this approach can reproduce many things here, and we can explain many things. For example, experiments exhibit relatively low amplitude correlation. We can argue why it is. That's because there's segments quite low, maybe there is a low rate of charge hole diffusion, and so on. So you can explain many things here. And remember, I mentioned there is experiments also were done with different electric fields. And again, we can explain. So this is experimental observations. This is experimental observations on lengths. And you can do the things. If this is in our theory, we can assume if there is external field, then it will affect the diffusion rates differently. And you can calculate things. So the dots are experimental points, the line is our theory. Again, which comes from this very simple stochastic theory. And we can explain why communication distances get cosine dependent. That's because you can really expand exponential function, and the small parameter will be cosine function. Again, this is our experimental points, and it feeds experimental data, and it works quite well. So the simple theory can capture a lot of things here. The simple stochastic theory can capture a lot of things here. So, for example, it can also capture the strength of the voltage. So in this experiment, you can also change the strength of the voltage and measure quantities, and that's what is shown over here. This is communication distance as a function of the voltage. Red points experiments, the black line is the theory. Okay. So you can explain many things successfully. But one of the most important things was this universality observation. To remind you, there was a surprising universality observations that doesn't matter how you change, let's say, laser strength, size of the lattice segments, concentration of substrate, this communication distances or communication depths were the same. The theory can explain the thing. That's because the most important quantity is this quantity, this length, right? Which is the square root of diffusion coefficient over death rate. So all of these things like laser intensity, catalytic activity, details, they do not affect anything. So anything that do not affect this will not change communication length. Again, I want to emphasize it comes from a very simple stochastic model, essentially single particle stochastic model. Okay, so and again, the advantage of the theory. So the most useful theories are not the right theories, but those that can give specific predictions that can be tested experimentally. Okay, there is no value to explain the data if your theory if you cannot propose testable predictions. So this is the advantage of the theory. The theory has a specific predictions on the dependence of the temperature. Again, we're using something that I mentioned to you before, this idea of Arrhenius rate. The rate can change arenas change. Okay, so essentially this is stochastic theoretical approach, can provide explanation to all experimental data. It explains naturally universality. It explains natural universality because those things that determine cooperativity do not depend on many of these details of experiment. Okay? And you can give quantitative predictions that can be tested in a future theory. So this is again an example of stochastic theory, but what is important here to do is that when we talk about any theory, you have to be critical to yourself. Okay, so in other words, I'm not a car salesperson. Okay, I'm not trying to sell you the car or whatever, cosmetic, whatever. You probably people in the business oriented world, right? We're doing science, so you have to be critical to yourself. So you have to understand any theoretical picture. There is always a limited one. There is always limitations. So this is a mesoscopic approach. Okay, there is no explanation how things happen microscopically. So I made some assumptions. I assume something. I assume that the reaction rates are determined by the local concentration of holes. I assume that these holes diffuse, but why? I don't know. Okay, so the theory is mesoscopic. We need to have more microscopic theory to explain why it's happening, but that's probably beyond of my expertise. You need to know at quantum mechanics. I only consider one-dimensional system. I justify this. The effective experimental setup was one-dimensional. You can do it for other dimensions. Another important assumption, which was I assumed that you quickly go to stationary state, right? Of course, it was easy to solve because instead of differential equations, I get algebraic equations, but maybe that's not the case. And then, of course, I criticize theories because I assume that everything is uniform, but I use my self-uniform assumption on the rates. Catalysis, real catalysis will be probably not uniform, will be much more complicated. So is it really the case? Not clear. Again, and this is classical description. So you know about quantum mechanics, right? In principle, quantum mechanical phenomena might be important here. Here I neglected quantum mechanical. I assumed that these particles, they actually diffuse classically, very similar to Tassel models, for example. In any particles, they diffuse, and that's what enough to explain the norm. Okay? So, again, I'm actually moving too fast. So this is, we introduced stochastic hypothesis. I want to emphasize, right? The stochastic hypothesis that particle can be produced randomly at given locations, can diffuse and can, but this eventually can explain all the derivation. So you can see that this charge holes, the charge particle, they are simulating reactions. So in other words, this cooperativity is a result of that at given location you can, in principle, randomly produce these particles. These particles can diffuse, and if they diffuse, they stimulate reaction at another location. That's the idea. Stochastic idea, but works reasonably well. And again, I want to emphasize that this is a stochastic model which you can analytically analyze and provide actual agreement with experimental observations. And there's a testable prediction. Again, I want to emphasize that stochasticity was important here. It was important. And despite the fact that everything was random, the outcome was quite predictable. You can predict what is the cooperativity, you can predict the length, you can predict the time. Okay? Again, I'm talking too fast. So this is essentially the story. Again, I don't want to put too many stories in one. So this is the first story. It's a chemical story. I try to give you as much as possible background. But if something is unclear, please let me know. Feel free to ask me. This is it.
So if we will generalize the concept to two dimension, or maybe the way we do it in KLS models, where maybe a site can have more than one particles.
Yeah.
And then is it like going to be like the figure 1A, this A part? So is it like diffusion? If they will compete for the diffusion among ourselves, so is it going to change
there will be effect of dimensionality, will be effect, but it will be. I think we did some calculation. We didn't publish it, but there will be some effect of dimensionality. Yeah.
But the generalized results will be the same.
Similar. Will be maybe size will be smaller.
Okay.
But the results will be the same. We generalize these two other possibilities. We included more random. Suppose the rates are random. So we did something similar to what you did with the set. So one extension was suppose the rates that give random, spatially random at given location at different rates. But then we suppose rates are random as a function of time that fluctuate. So there are, you can calculate many things here. The problem was experimentally is impossible to do, almost impossible to do things, but we did extension in several directions. Okay. But again, the conclusion is you can have a stochastic approach, very simple, which can explain the phenomena. And I want to emphasize again that it was really essentially the same master equation, right? Let's go back to. This is the same master equation that we talked about, right? It's essentially solving this master equation that allowed us with some additional few conditions allowed us to obtain these things.
So, for example, for this is the simplest model, I think so you have it, the way you have only one kind of catalysis.
Yeah.
For example, if we have a system or a film where we have two kinds of catalysis also. So one of catalysis one is going to oppose the second catalysis, but it will favor or having the cooperative effect with its type one. So that is also can be incorporated.
Yes, all these complexities can be included. The most difficult things, experimentally things are very difficult to do. So the question was experimentally posed the question: is this cooperativity where it comes from? So, and this is the answer. The possible simple picture can explain where it comes from. Any questions? Too much chemistry, huh?
So in biological motors also show the cooperative effect with each other.
Yeah.
Isn't also like the kinesin of what I have seen that in one paper that kinesin diamond they oppose each other, but they support their own time.
Cooperativity is a story which is common in many biological processes. But here it was surprising, right? So remember, that was a catalyst. So the catalyst has some active site, place where reaction happens. And it should be completely random, right? So the molecule comes from right? Completely random. So there is not clear why there is a cooperativity. So that was much, in biological world I can explain and give more. Here it was much more harder to explain.
Somewhere related to, let's say, we have two-dimensional surface, which is that microscopically it is rough. So there will be dust particles, so they will be saturated over here. Is it going to be something like the action happening or catalyst happening as depositing a dust particle on a particular site?
So I think it's not, because you see, these reactions are product always fluorescent labeled, so you can always see the reaction. So all this bright spot corresponds to reactions, and the brighter one, more reactions in this location. So this single molecule measurements were convenient from the point of view that you could really visualize reactions in different locations. Okay, so that was the advantage of using single molecule, because you can clearly visualize it and distinguish. This is a real phenomena. It's not. Okay.
Fine. Yes, thank you.
Thank you so much. Okay. So sorry. Yeah. I didn't want to give a long story. So
Thank you.